All right, today we're going to go on a little journey, right inside the mind of a machine. We're going to follow one single piece of data as it travels through a feedforward neural network, one of the absolute core building blocks of AI, to see exactly how a decision actually gets made.
It really all boils down to this question, right? Now, a real thought is, well, it's incredibly complex, but we can peek behind the curtain on the basic mechanics by looking at a simple but really powerful AI model. We're going to follow a single piece of data on its journey, all the way from raw input to a final calculated decision.
So the model we're exploring is the Feedforward Neural Network, or FNN for short. And at its heart, it's basically a one-way information highway. Data gets on at the entrance, it travels forward through a series of checkpoints, and then it exits at the end. That's it. There's no turning back, no loops, and absolutely no memory of what came before. To really make this stick, we're going to follow one tiny piece of data on its journey down this highway. We're going to see every single calculation and every decision point, starting, right now, at the entrance ramp. Okay, so here's our data. For our journey, it's just two numbers, 0.6 and 0.2. You can think of these as raw features. I don't know, maybe the brightness of a pixel is 0.6 and its size is 0.2. This is the only information the network has to work with as it enters the highway. So our data has just arrived at its very first checkpoint, a single digital neuron, tucked inside what's called a hidden layer. Now this neuron's whole job is to take our input and decide how important it is. And it does this in two simple but really powerful steps.
First up, the neuron calculates what's called a weighted sum. It's basically mixing our inputs together, but not equally. It gives more weight or more importance to some inputs over others. Then, second, it uses an activation function, which acts like a gatekeeper, to decide if this combined signal is strong enough to even pass on to the next neuron.
Let's actually walk through the math right here. Our first input, 0.6, gets multiplied by a weight of 1.5. Our second input, 0.2, gets multiplied by a negative weight, negative 0.7. Now, you can think of these weights as the neuron's learned opinion. It has learned over time that the first input is positively important and the second one is negatively important. We add those weighted inputs together, and then we add a tiny bias of 0.1, which is kind of like a final nudge to the result. This gives us our combined signal.
And boom, the result is 0.86. This single number represents the neuron's initial take on our data, combining all the inputs and their learned importance. But the journey is not over, not even close. Now comes the most critical part of the whole process.
So now we get to that second step, activation. This is the spark. This is where the network gets its real power. It's not just about adding numbers together, it's about making a decision. Now you might be asking, okay, but why? Why do we even need this extra step? Why not just pass the 0.86 along? Well, the answer is the secret sauce to what makes these neural networks so incredibly capable. And this slide shows you exactly why. Without a nonlinear activation step, the entire network, it doesn't matter how many layers it has, it could only ever learn to draw straight lines through data. It's totally limited. But adding that activation spark introduces nonlinearity. And this is what lets the network learn and trace these incredibly complex, curved patterns. You know, the kind of messy, unpredictable patterns that we actually see in the real world. In our case, this neuron uses a really common activation function called ReLU. And its job is super simple. If the number coming in is positive, let it pass through. If it's 0 or negative, block it and send a 0 instead. It's basically an on-off switch. Since our weighted sum was a positive 0.86, the neuron's final output is 0.86. This value now moves on to the next checkpoint in the network.
Now just imagine that simple calculation happening hundreds, maybe even thousands of times as our data point zips across multiple layers of neurons. After passing through all those checkpoints, it finally reaches the end of the highway, the output layer. This is where the network makes its final prediction.
What's really fascinating here is that the end of the highway is custom built for the journey's purpose. As you can see here, if the network's job is a simple yes or no choice, like is this a cat, it uses a final layer called sigmoid, which just squashes the output into a probability between 0 and 1. If it has to choose between multiple categories, like is this a cat, a dog, or a bird, it uses a function called softmax, which gives you a probability for each of those options. And if the goal is to predict a specific number, like the price of a house, it might just use a simple linear layer. The network's final action is always tailored to the question being asked. So now that we've followed our data from start to finish, let's zoom out for a second. What is this kind of one-way, memoryless journey actually good for? And, just as importantly, where does it fall short?
FNNs are simple, they're fast, and they're great with structured data. Think of the rows and columns in a spreadsheet. But their biggest limitation is built right into their design. Because it's a one-way highway with no memory, it can't understand sequence. For an FNN, the sentences "dog bites man" and "man bites dog" are just bags of words with no difference in meaning. It also can't understand the spatial layout of pixels in an image.
And this really puts it all in perspective. The FNN is a powerful and essential baseline, but for complex data that has a sequence or a spatial structure, you just need other tools. To understand language or images, you need networks with totally different architectures, ones that are designed with memory or with 2D vision, which an FNN simply doesn't have.
So, if you're working with FNNs, it is crucial to avoid a few common pitfalls. First is overfitting, which is where the model basically just memorizes the training data instead of learning general patterns. The second is making sure your inputs are scaled properly. You don't want age in years to overpower height in meters just because the number is bigger. And finally, as we just saw, you have to match your output layer to your specific problem or the network just won't know how to learn properly.
And that leaves us with a final thought. The feedforward network's journey is a straight line, processing each piece of data totally in isolation. It sees the world one moment at a time. But what happens when we break that rule? What happens when we give a network a loop and a memory? Well, that's where things get even more interesting.